Yes, a very good morning to all of you. Am I audible and visible properly? Yes. Okay, did you people check your results? I hope you people excelled over there. Yes. Hai na, Suhas, if had it been the case you are AIR 1, you won't be here. Hai na? So tell me such kind of ranks which I can't catch. Okay. Anyways, good. 400 above. Fine. Not an issue. Okay. Anyways, I think in the last class, I think we have finished off with the entire periodic table chapter, right? And now we are going to start off with a new chapter, okay, which is chemical bonding. Okay. So in chemical bonding, again, chemical bonding is very, very important. Okay. And let us begin this chapter. And whatever you have learnt in case of periodic table, definitely it is going to help you out in chemical bonding. So each and every chapter is related. Okay. So let us begin that without any further delay. Disable data. So today we are going to study about chemical bonding, which is one of the very important chapter as far as your entire chemistry is concerned, right? Now, when I say, like, how do you define a bond, right? So what is the definition of it? So suppose if I say that I have got a molecule where it is like AB is there and they have brought 2 electrons, okay? So one electron from each side and they are sharing it, right? So these electrons are like keeping these two like species, that is A and B, together. So what is that? Electron. So electron, there will be like force of attraction between the electron and the nucleus of those 2 atoms which are there, right? So ultimately, if at all somebody is asking me about bond, so I can say that it is the kind of force of attraction which has kept these 2 atoms together there, right? Similarly, if at all I am having like A plus and B minus kind of thing. So here like one species, A has lost the electron, B has gained that electron, right? And they have formed the cationic and anionic species, right? After forming the cationic and anionic species, are they having this force of attraction, which is electrostatic force of attraction, right? So this electrostatic force of attraction is the thing which binds them together, these 2 entities or these 2 ions together. So that is also called as a bond. So in general, if at all I have to say what is a chemical bond, so basically it is the attractive force which is holding these constituents. Constituents, when I talk about, they are basically atoms or they could be ions, right? Together in different chemical species, because A and B, they are going to be different chemical entities or the species, right? So I hope this definition is clear to you, okay? So let us write down the definition of it. So the attractive force that holds the constituents, the constituents could be atoms or ions together in different chemical species, That's what is chemical bonding. Okay. Now let us try to understand a very simple phenomena of formation of H2 molecule to relate to this thing particularly. Right? H2 molecule will be formed how? By one hydrogen atom, another hydrogen atom which is there. One electron is there with this hydrogen, one electron is there with this particular hydrogen, and they are going to like kind of share it and make the bond there, right? Now that particular bond formation thing, it could be explained in terms of the potential energy graph. So here if at all suppose I am writing energy, here it is 0, here it is positive, here it is negative, suppose, right? Definitely below 0 it will be negative, right? Now the nature of graph which seems here is something like this, right? So let us talk about the scenarios here. Now suppose you are having 2 hydrogen atoms at the first instance. Basically, we are going to see how the bond is getting formed here, right, in terms of energy. Okay. And imagine that first of all, these two hydrogen atoms which you had, they were very, very far away from each other. That means there is no interaction between these two hydrogen atoms. Okay. So if at all I show that particular nucleus by the bigger dot of two hydrogen atom and one electron, are you able to see that? One electron. So this bigger dot is telling you the nucleus of one hydrogen atom, and this is the electron present in that particular hydrogen atom, right? Rather than, writing like this, a nucleus and the electron, what I'm writing is a bigger dot telling you the nucleus and one smaller dot which is telling you basically the electron. Now, do we know the formula of potential energy? That is minus K Q1 Q2, or else just K Q1 Q2 upon R we are having, right? K Q1 Q2 upon R. Now, what I said in the first position, you imagine that those two hydrogen atoms which are trying to come closer and form the bond, at present at the first position they are very, very far away from each other. That means let us take this R as infinity. If I take R as infinity, then the potential energy is going to be 0. So are you able to see at the first instance this curve is almost parallel to this, or else almost touching it, right? So that is the first scenario. Okay. Now what happens is definitely they'll still keep on coming closer, right? So when they keep on coming closer, so there are basically two kind of forces which will be operating, right? So what are those two kind of forces? Can you guess that? What are the two kinds of forces? Definitely when two atoms, these two hydrogen atoms, when they are approaching each other, so there will be like attraction which will be developed between the electron of one atom and the nucleus of other hydrogen atom. Vice versa for the other one also, right? And there will be like repulsive interactions also. That means between the two nucleuses, there will be repulsion. Between the two electrons, there will be repulsion, right? But if at all they are still coming closer to each other, that means the force of attraction here is dominating slightly over your repulsion, right? So here, if at all I come down to the second one, where force of attraction dominating, that means potential energy is going to decrease. So here you can understand that at this time, they are closer by. Here I am writing this nucleus and this. So there is a force of attraction which is between this and which is between this. Are you able to understand? This is of one hydrogen atom, this is of another hydrogen atom. So nucleus of this is attracting the electron of this. Nucleus of the other hydrogen atom is attracting the electron of other one. Now what happens is slowly they'll try to come closer to each other to such an extent that the force of attraction and force of repulsion, they balances out each other, and these two atoms at that time, they enter into bonding with each other, right? So basically at this scenario, this is like third one. Here I can write down, this is case, this is the other nucleus. This is like bonding has happened, right? So minimum potential energy, so maximum stability. Are you able to see the minimum negative here, right? So that's how minimum energy means the system has attained the stability there, okay? Now the thing is, it has entered into bonding. So I'll call this as like bond length of hydrogen, and that comes out to be 74 picometer. Now, if in terms of energy you talk about, that since I told you that, energy got released when they have entered into bonding. So how much amount of energy has released? This is given by 436 kilojoule per mole, right? So this much amount of energy will be released when two hydrogen atoms which are isolated, they combine together to form molecule, right? So this I call it as bond energy of hydrogen. Then suppose after third, if you still try to bring them closer, if you keep on decreasing this distance, this is basically what we are writing is the internuclear distance, okay, on this axis. Getting it? This axis is internuclear distance and this one is of energy. Now, if you keep on decreasing that internuclear distance beyond this 3, what is going to happen? You are bringing it too closer, right? Already there is a scenario at third where the force of attraction and force of repulsion, they have balanced each other. Now, if you bring it too closer, then the force of repulsion dominates. These two atoms will, bond will break and these two atoms will run away from each other, right? So there is no bonding there. Bond breaks there, okay? So here we say at the fourth position, you are having like this. In fact, I can draw something like this. Nucleus, you are having one electron here. So they are running away from each other. So we are saying nuclear repulsions are there. Okay. So suddenly the energy of the system has increased. Got it? So that's how bonding phenomena happens. Quickly copy it down. Yes, I hope it is written. And this data is specific for the hydrogen, bond length for hydrogen only. That means when these two have entered into bonding. So this distance I am talking about. This is the bond length. I hope it is clear now. Now let us go for the types of bond. When I talk about the types of bond, and I'm having three types basically. You are having ionic bond, you are having covalent bond, and you are having metallic bond. Right. Now let us try to see the characteristic of all these three, right? As such, you'll be having slight idea about this, right? Ionic bond, definitely it will be formed between the ions. That means cations and anions. Covalent bond, it will be formed by sharing between the two either like atoms or unlike atoms. That means similar or dissimilar atoms, right? What about this metallic bond? The bond which is present in any metal. That's what is metallic bond. Okay. So let us make one particular table here. So we can write down general characteristic, and we can have ionic bond, we can have covalent bond, and we can have metallic bond. First thing, we are going to see the definition of it. So basically, ionic bond is formed between a cation and anion. So definitely, if at all cation and anion is involved, that means what is there? There is transfer of electrons between one atom, between an electropositive atom and electronegative atom, because who will be forming cation? Those who are easily able to lose electron, and that is a characteristic of a metal, and metals are electropositive, right? So we are going to write down formed by transfer of electrons between electropositive and electronegative element, right? So I'm writing here what is EP basically, electropositive, and what is En, that is electronegative, right? What about covalent bond? Formed by sharing of electrons between two similar or dissimilar atoms. Okay. Then what next we are having for metallic bond? Basically, there is one electron C model, according to which it is said that the positively charged core, positively charged core, that is kernel, is embedded in sea of electrons. What do you mean by that? Suppose I am talking about aluminium, right? So basically there are like more than one theories to explain metallic bond, and the simplest one being the electron C model. Okay. So what it says, suppose I want to understand about aluminium as such. And for the aluminium metal, what kind of metallic bond is present? So what you are having is aluminium, it can be formed like it can lose 3 electrons from its outermost shell because it is having 3s to 3p1, right? Now, when it can lose 3 electrons, so whatever is like inner electrons and along with the nucleus, that particular portion I am calling it as positively charged core, which is also known as kernel. Okay. So what I'm saying here is, so you are having all these positively charged kernels occupying the lattice sites, right? Al plus 3. They are basically crystalline in nature, so they'll be having the lattice over there. Now the thing is, these electrons, like 3 electrons which have been lost by each and every aluminium ion here, basically they'll be like free to move around in the entire crystal volume, right? So that is the reason we say that basically in the sea of, it seems like it is a sea of electrons, and in that you are having positively charged core which is embedded. That's what is metallic bond. And basically it is the force of attraction between these electrons and the positively charged core which is keeping it intact there, right? I hope it is clear to you. Okay, now let us go for the next one, that is constituent particles. Now when it comes to constituent particles, here it is cations and anions. That is, you will be having a metal and non-metal, right? Here, like or unlike atoms. And here you will be having same atoms. That means atoms will be there. For aluminium, you are having aluminium only, right? Then, crystalline nature. When it comes to crystalline nature, they are crystalline, okay, in solid state. Now, amorphous. They are amorphous except for few giant molecules which we know. I'll do one thing, I'll just write down here properly so that we have proper space. Same atoms. Here amorphous except certain giant molecules or three-dimensional network which they have. So giant molecules like diamond, SiO2, silica, etc. These are crystalline. Now when I talk about crystalline and amorphous, you must understand crystalline means there is regular arrangement of the constituents there. So if at all I'm talking about ionic compound, so ionic bond or else ionic bond is, it will be present in the ionic compound. So you are having cation and anion, and already you might have little bit idea about around 1 Na plus there are like regular arrangement of 6 Cl minus. So around 1 Cl minus there is like 6 Na plus which are arranged. So that arrangement is present throughout the entire crystal lattice, right? So that's what is crystalline nature. Okay. Now when it comes to amorphous, so amorphous is like, it's not a regular arrangement or else up to only short range the arrangement is there. Okay, regularity is there only for the short range. Now here they are crystalline in solid state. Crystalline in solid state. For metallic, they are also crystalline in solid state. Okay. Now, after crystalline nature, let us go for melting point and boiling point. This is going to be very high. Why very high? Due to electrostatic force of attraction. Electrostatic force of attraction between the ions, right? And here, in this case, it is low, except for giant molecules, which I have written three-dimensional network, which have three-dimensional network, right? And what about metallic? This is low to high. So low in case of mercury we know, because it will be like atom temperature liquid, and high in case of iron we can understand. See, try to understand this property, which is melting point and boiling point. What we are saying is, when you try to melt something, that means from solid you want to make it liquid, so you are giving energy, right? So suppose now my ionic compound which is there, in which ionic bond is present, there, if at all there is electrostatic force of attraction, strong force of attraction, right? So to make them get into the liquid phase, you have to give more amount of energy to them, right? So that's how the melting point is going to be high, and even the boiling point is also going to be high. If the force of attraction is less, then you just need to supply less amount of energy and your job is done there. Here it all depends upon what kind of metallic bonding is there, okay? So you will come to know later on, but at present you can just understand in case of Hg, it is contributing less number of electrons to that particular electron C. Because of that, we say that it's having low melting point and boiling point. In case of iron, more number of electrons can be contributed from iron to the electron C, right? And that's how strong metallic bonding there. Okay, so you will eventually learn, don't worry about it. Then next property is mechanical property. That means we are talking about like hardness here. So this one is hard but brittle. This one is soft except the giant molecules. Giant means three-dimensional network, hai na? Giant molecules, which are basically very hard in fact, and they are like soft to hard. Soft alkali metals, you know alkali metals, and hard you can have D block element, right? So you understand, I have written this one as hard but brittle because the thing is, again, force of attraction only is dominating here, so that's why it is hard. But why it is brittle? Suppose if I give you something like arrangement of this Na plus Cl minus, here also Cl minus, Na plus Cl minus, Na plus, right? Here also Na plus, let us say like this, okay? Now if at all there is any kind of force which is applied, suppose I take a hammer and I apply the force, so what will happen? This thing will be like dropped down, okay? This can move down. So if it is moving down, you are having Cl minus facing another Cl minus, so there will be repulsion and it will break. So that's why it is hard but brittle, because on application of what? On application of a particular force or any kind of stress there, it is like breaking down. Here they are soft, but except for the giant molecules, diamond and all those things, they are very hard. Hardest known substance, okay? Now, soft, you know that sodium can be easily cut from the knife also, but iron you cannot cut, okay? So they are hard, okay? Fine. Now let us move on to the next one, which is basically solubility. So ionic compound, they involve ions, there is polarity there, so they will be soluble in polar solvent, right? So soluble in polar solvent. Soluble in polar solvent. Here they are soluble in non-polar solvent because there is no polarity here, or very less, na? Soluble in non-polar solvent, and here they are soluble in metallic solvent. Now when I talk about metallic solvent, I'm basically talking about basically the amalgams, you know? So suppose I'm having zinc mercury amalgam, that is basically the metallic solvent. Then next is directional nature. So here this is non-directional. This is going to be directional. And this is again going to be non-directional. Right? Directional nature in the sense, see here you have little bit idea that whenever covalent bond is getting formed, definitely we say on the very basic level that okay, electrons are being shared, but those electrons are present in the atomic orbitals, right? Which undergo hybridization and then there is overlapping, right? So you can think of that those are like directional, they'll be pointing in a particular direction, right? All the atomic orbitals which are there, suppose px, py, pz if I say, so they're pointing in a particular direction, right? So it depends what is the internuclear axis along which I am bringing them and we are forming the bond. So it is directional. This non-directional because it involves the force of attraction. So attraction doesn't have a particular direction. Similarly, here also, it is also involving the attraction between the core, positive charge core, and you are having the electron. So it is also non-directional, right? Now, let us see one more property, which is basically here, conductivity. So whatever ionic bond is going to be present in basically ionic compound. So they are going to be conducting only in molten state, okay? Or else in their solution phase, but they are never going to conduct in case of what? In case of solid state, okay? So you can write here non-conducting in solid state, conducts in molten or solution phase. Here, not conducting or else non-conducting except for graphite. And here, they are going to be conducting in solid as well as molten state, right? They do not conduct in solid state because the ions are having their fixed location, right? So because of that, the ions are not moving. But when you melt it, molten form or fused form, or else when you make the solution of it, ions try to move. Getting it? So conductivity will be there. Make a note of all these things, all of you. Then we'll proceed further. Yes, I hope it is written. Now let us go for analyzing each and every bond here. So ionic bond or electrovalent bond. Now when I talk about ionic bond, basically ionic bond will be formed by the transfer of electrons, okay? So we can say the bond which is formed by transfer of electrons between two atoms is known as ionic bond, right? Electrovalent bond, why we are saying is because see the thing is electro word is related to electricity, which means charge, right? Valent means basically valence, right? Valence electrons we are talking about. So basically if the electrons are being lost from any atom, they are lost. The electrons which are getting lost, they are valence electrons, and the electrons, if at all they are being gained, so they are also entering into the valence shell, right? So that's what is electrovalent bond. Now there is one more term which is electrovalency. So you can remember the number of, this is nothing but the number of electrons lost or gained by any atom, right? So let us try to understand this. Suppose if I talk about sodium, and we are having chlorine also, right? And I'm going to make NaCl using them. Okay, I'm not saying that Na combined together and Cl like that. So basically we can have something, if at all it is confusing, you can write like this. For sodium, what we write down? Neon 3s1. For chlorine, what we write down? Neon 3s2, 3p5. So it is just 1 electron short to attain the octet, and if it loses, it will have the stable configuration like neon. So what happens here is this Na loses 1 electron to form Na plus. It will have the neon configuration, and this accepts 1 electron from that Na plus and forms this. This one will become what? 3s2 3p6. I can write down like this: neon 3s2 3p6, or else I'll write down this as argon, configuration of argon, right? So that's how these two, they will form basically NaCl, where it is Na plus and Cl minus, and the electrostatic force of attraction which is there, which is binding them together. And the bond which is present between these two, I am calling them as ionic bond or else the electrovalent bond. If you see here, sodium has lost its valence electron, and the electron which is there, it has entered into the valence shell of it. Okay. Now, if at all I ask you, what is the electrovalency of Na plus? So it will be, in fact, electrovalency of Na, it is 1, and electrovalency of chlorine, it is also 1, because it has gained 1 electron. Getting it? Similarly, I can have MgO, like this is like neon 3s2, and you can have like oxygen, which is neon, helium 2s2 2p4, right? It needs 2 electron, and it needs 2 electron means it wants to gain 2 electron, and it needs to lose 2 electron, right? So what will happen here? It will lose 2 electrons and form neon configuration, and it will be like Mg plus 2 I am writing. This will gain 2 electrons and it become O minus 2, and I'll be able to write this as helium 2s2 2p6, or else I can say that it is neon. So both of them, they have formed what? MgO, which is ionic compound, Mg plus 2 and O minus 2 there, right? So what is the electrovalency? Electrovalency of magnesium and oxygen there, both of them 2, right? Now hopefully you people have understood this one. Now let us see conditions favorable for the formation of ionic bond. Okay. Okay, I'm giving you some time to copy. Please copy this. I think this might be remaining a little bit. Copy this and let me know. And once we are done, you can do thumbs up so that I can understand from here. Okay. Fine. Yes, I hope it is done now. Now let us go for conditions favorable for ionic bond. See, in case of ionic bond exists between a cation and anion, right? So cation who will be forming, it will be the metal which is forming the cation, right? So how easily it can lose electrons? So it will be easily able to form the cation. That means losing the electrons, that means what? We should be easily losing the electron means it should require less energy to remove that particular electron. That means here I am talking about ionization energy. So first condition is it should have low ionization energy, right? You are having actually two entities here, na? A plus and B minus, right? So if at all I am saying that there is going to be ionic bond present between cation and anion, right? So whichever is the metal, suppose A, it should be able to form A plus easily. Easily means with less requirement of energy. And to make A to A plus, I need to supply energy, and that energy is known as ionization energy, which we have already studied in periodic classification. Okay. Now, there will be like another anion. I have to form from a neutral atom, I have to form anion. So how easily or like nicely it accepts the electron? That's what is electron affinity, right? So the thing is, if it is easily accepting the electron, I say that it has to have high electron affinity. EA is electron affinity. Okay. Now, next thing, high lattice enthalpy. Lattice energy or enthalpy. First, you write down these conditions, then I'll tell you what is lattice enthalpy. Okay. Now, let us learn about lattice energy over here. Now, when I talk about lattice energy or enthalpy, so let us say, I'll say that I have taken 1 mole of this NaCl solid, right? And how much energy I should supply so that I can break this 1 mole of the ionic compound or ionic solid into its constituent gaseous ion, right? And it's about 780 around, okay, kilojoule. Now, what I said, what is lattice enthalpy? See, the thing is, what I'm saying is, for this ionic compound only you define lattice enthalpy, because I said that they are crystalline in nature and they will be having a particular crystal lattice. What do I mean by particular crystal lattice? That means in that lattice, you'll have the cation and anion arranged in a proper way, or there is a kind of arrangement which runs throughout the lattice. Okay. Now what you're having is, I define my lattice enthalpy as, there will be force of attraction, right, between those cation and anion, right? Now, if I want to break that lattice, I need to supply energy because I have to overcome the force of attraction over there, right? So what I'm saying, the amount of energy which is required to break 1 mole of the ionic solid into its constituent gaseous ions, because I am having Na plus and Cl minus as the ions over there, right? And they are the constituent ions which are making your NaCl, right? So that's what is the definition of lattice energy or enthalpy. So let us say delta H for lattice, or else lattice enthalpy. Let us say some amount of energy will be liberated here, right? Around 780 it will be liberated, but I'm just writing negative. Some X amount is getting liberated, right? So I can write down here the amount of energy required to break 1 mole of ionic solid into its constituent gaseous ions, right? So write down this definition. Now there is one more way in which I can, kind of, here delta H is going to be positive because I have supplied energy, right? It's an endothermic process. Did you understand? Please make this as positive because I have supplied energy to it now to break it, right? I can also reverse this. That means Na plus gaseous plus Cl minus gaseous to form NaCl. Now this time lattice energy is like negative here, or else delta H lattice, if at all I am writing, that is negative. right? So what I can define, normally it is defined in this way only, right? Majority of the cases, but the other way also you should know. Other way is the amount of energy. In this process, it was required. You have to supply. Now, when I have reversed the reaction, that the same amount of energy will be liberated, right? So what I've written here is the amount of energy released when 1 mole of the ionic solid is formed from its constituent gaseous ions, right? So that here amount will be released. There it was required. Suppose 780 kilojoule was required to break. Here it is minus 780 will be liberated. So here I can also say another definition. The amount of energy released when 1 mole of ionic solid is formed from its constituent gaseous ions, right? So I've just reversed it. Okay, now lattice energy is basically K Q1 Q2 by R, I can write, mathematically, if at all I have to say. So basically it is K Q1. K is again your Coulomb's constant. Q1 Q2 we are writing, right, which is the product of the charges. R is the size, and here this R is basically RC plus RA, that is the radius of cation, and here you are having the radius of anion. So it is taking care of both the radius, that means of the cation as well as of the anion. Okay. Now we are just trying to see the factors which affect the lattice energy. So I've directly written the formula for it. Now the thing is, I can say lattice energy is directly proportional to the charge. And when we are talking about charge, we are just referring to here the magnitude of those charges. And lattice energy is inversely proportional to the size. Right? From this particular formula only we are seeing this. Right? So suppose if I ask you to compare the lattice energy of LiCl, KCl, or else LiCl, NaCl, KCl, right? You know here Cl minus is fixed. What is changing? Li plus, Na plus, K plus. Down the group when I move, size increases. So what happens to the lattice energy? It should decrease. Now, if I give you something like NaCl, MgCl2, and you are having AlCl3, right? In this case, what are the charges here? +1, -1, here +2, -1, crisscross, Mg +2 and Cl minus. Here Al +3 and -1. So what is the product of the charges? If at all I have to write down Q1, Q2, I just have to consider the magnitude of it, not the sign. So it will be 1, here it will be 2, and here it will be 3. So are you able to see charge is increasing this way? Product of the charges. And what about size? Na plus, Mg plus to Al plus 3. Isoelectronic species, no? So higher is Z value, smaller will be the size. So in that case, smaller size, higher lattice energy, more is the magnitude of the product of charge, then also higher lattice energy. So it is always indicating here. Getting it? Now the thing is, how do you relate this high lattice enthalpy with the strength of the ionic bond? If at all I am saying there is high lattice enthalpy, I say that the strength of the ionic bond which is there, it is more. What is this lattice enthalpy? How much energy is required to break that particular lattice? Or else 1 mole of that ionic solid into constituent gaseous ions. If higher will be the force of attraction between them, that means higher is the strength of that ionic bond. Then you have to supply more energy to break that bond, right? So we are saying that higher is the lattice enthalpy, higher will be the strength of the ionic bond. Okay. So I'm going to write down here, higher is the lattice enthalpy, higher will be the strength of ionic bond. Pen. Okay, got this? Higher is the lattice enthalpy, higher will be the strength of ionic compound. Ionic bond there, okay, which is present in the ionic compound. I hope you people have written this. Now next is covalent bond. When we talk about covalent bond, basically covalent bond will be formed by what? Sharing of electrons, right? Between either the two like atoms or between two unlike atoms, right? So we can write here the bond which is formed by sharing of electrons between two like or unlike atoms. That's what is your covalent bond. Okay. Now, if at all I talk about, basically, let us say hydrogen. So, how in this case of hydrogen, I am having one hydrogen atom with one electron. So, basically, what has happened? Hydrogen can never achieve octet, basically, right? So, basically, when these two hydrogen atoms combine, they are going to share one electron each, right? So that they can attain the duplet configuration like helium, which is 2s2. Sorry, which is 1s2, right? Are you getting it? 1s2. So basically, I'll be writing like this. For making one bond, you require two electrons. So basically, when one pair of electron is being shared, you will be getting a single covalent bond. Okay? This is single covalent bond. Now, if at all I talk about O2, so in case of oxygen, in fact, before this I can give you one thing. Lewis dot symbol as such but still for a safer side, we'll write this. There's nothing, no harm in that. Let us just write down Lewis dot symbols, so that you can relate to it in a better way. I'll definitely write that hydrogen again, right? Because some of you, if at all not aware, that is the reason I just want to give this first. So what is this Lewis dot symbol? It represents the number of valence electrons present in an atom. Okay. So if at all I am writing like lithium, there is only one electron there. Valence electron which I am talking about. 1s to 2s1 we write now. So we are just representing the valence electrons. Beryllium, there are two. Boron, carbon, nitrogen, oxygen, fluorine and neon. So this is like how many electrons here in case of neon? 8, right? In case of boron, you are having 3. In case of carbon, you are having 4. In case of nitrogen, you are having 5. In case of oxygen, you are having 6. In case of fluorine, you are having 7. And in case of neon, you are having 8. So all those valence electrons are being shown by a dot, which is known as, they were like Lewis dot symbols, right? Now, let us see here. Basically, if they are tall, they are sharing also, they are sharing that valence electron only, okay? Now, I have written for hydrogen, H2. In case of H2, you are having one hydrogen with one electron, another hydrogen with one electron. They're going to share one electron with each other so that they can have this duplet like helium, which is 1s2. So you'll be able to write this as HH, and I'll be saying that this is basically single covalent bond, right? Similarly, I can give you the example of O2, where what you are having is two oxygens, right? Each oxygen is having 6 valence electrons. Their octet is not complete. Basically, they are sharing electrons. Any species, either they are losing electron, gaining electron, or else they are sharing electrons. They just want to attain that stable octet configuration, like inert gases. Okay. So here basically what happens is, this is having only 6. So it is going to share 2 electrons with the other one. Here also it is going to share 2. So how many total pairs they have shared? Total 4 electrons have been shared, right? So that I can call it as they are sharing two pair of electrons. So it will be resulting like this. So I call this as double covalent bond. Right? Now, next I'm giving you N2. Suppose each nitrogen is having how many electrons? Valence electrons 5. So they are short of 3 electrons, right? So each nitrogen is going to share 3 electrons from each other. So basically they are going to share 3 pair of electrons. That means total 6 electrons. So I can write this as 3 electrons here. You can write down here as 1, 2, 3. You are having 1, 2 here. So basically this is what? 5 electrons of its own, 3 electrons here. Similarly here. So by sharing, those electrons are being counted for both of them. So both are getting benefited, right? So we'll be able to write like this. So this is triple covalent bond. I have given you very basic examples, need not worry about it. When we'll be learning how to draw the Lewis dot structure, definitely we are going to draw many more such examples, right? Very basic examples which you can easily relate to. Now, one more term which is here, which is known as covalency. Now, when I talk about covalency, I can say that the number of covalent bonds made by an element or atom is known as its covalency, right? Suppose if at all I take the example of SF6, right? Fluorine, fluorine, fluorine here, fluorine here, fluorine here. So how many covalent bond this fluorine is making? 6. So I'll say that its covalency is 6, right? Similarly, if at all I take S8, suppose, covalency of, if at all I ask you what is the covalency of sulfur in S8, right? So S8, basically we draw a crown-like structure. So this is sulfur here, sulfur, 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 all these bonds here. So one sulfur is making 2 bonds. Don't blindly say it is 8. So here covalency is going to be 2. Getting it? Please make a note of it. Yes, I hope it is done. Now let us go for the coordinate covalent bond. Or else I can even tell you this coordinate covalent bond later. Let us go for the various bonding theories at present, and when we are learning about the drawing of the Lewis dot structure, there itself I'll explain you about this coordinate covalent bond, right? So octet rule, right? This was given by Cosell and Lewis. These two were the scientists. Now basically what they said, that any atom, whether it is losing electron, it is gaining electron, or else it is sharing the electron, it is doing everything to attain octet in its stable configuration, right? Or else to attain octet, right? So that's what is this rule. According to this rule, the atom lose, gain, or share electrons to attain octet in their valence shell. Just like inert gases, because at that time there was nothing like advanced, and there were like not even compounds which were seen of inert gases. So inert gases, people thought that they are not reacting, that means they are self-satisfied, they are stable there. Okay. So if at all I talk about neon, argon, krypton, xenon and radon, right? And if at all I write down the valence shell electronic configuration, so we write this as 2s2 2p6 na? This is 3s2 3p6, this is 4s2 4p6, this is 5s2 5p6 and this is 6s2 6p6, right? So are you able to see that they are having octet? So rest of the atoms also, they want to lose, gain, share everything for the octet there. Getting it? So please write this, then we'll proceed further. And this particular octet rule or octet theory, whichever was that was valid only for the second period alert. It is valid or applicable only for second period elements. So just now we have seen in the previous case, Na is becoming Na plus, because what it is able to attain. Suppose sodium I took, so sodium was like what? Neon and 3s1. So if it lost one electron, it will become Na plus. It will become like neon, stable configuration. Cl was there. We wrote this as neon 3s2 3p5. Remember? So if at all I add one electron, if it accepts it, it will be becoming like argon, stable configuration, right? Now, in case of, suppose in case of O2, which we have seen. So O2 we have made like this by sharing of electron. So in this oxygen, there are like 8 electrons around it. Are you able to see? 2 bonds, so 4 electrons and 4 more, so 8 electrons. So either they are sharing, losing, gaining, everything to attain octet. Okay. Now let us try to learn the limitation of this octet rule. Now when it comes to limitation of this, see, first of all, it only talked about octet, no? Right? That means every central atom should be surrounded by 8 electrons according to them. But there were certain hypovalent species. Hypovalent means around the central atom, there were not 8 electrons. There were lesser than 8 electrons, right? So here, existence of hypovalent species, right? Now, hypovalent means the species in which there are less than 8 electrons around central atom. Okay. So basically, for example, BCl3 existed. You are having boron, chlorine, chlorine. Around this boron, you are having how many? Only 3 bond means 6 electrons, but this exists. You are having suppose AlCl3, that also the same scenario, BeCl2, BH2, right? So these are all, you don't have the octet complete for them, but they exist. So this octet rule could not explain this, how they are existing. Okay. Second one. So you can write this, existence of hypovalent species could not be explained. Here too we have just written the definition of it. Similarly, existence of hypervalent species could not be explained. And when I talk about hypervalent species, means species in which central atom has more than 8 electrons around it. Please write this, then we'll proceed further. Then hypervalent species like PCl5 is there. You are having SF6, for example, few. So PCl5, if you see, how many bonds around PCl5 or around this phosphorus? Basically, there are 5 bonds. So this is like 10 electrons. It's more than octet, right? SF6, fluorine, fluorine here, fluorine here, fluorine here also, and here also. So how many electrons around this? Basically 12 electrons. So more than 8 electrons there. So even it could not be explained. Why do they even exist at first place, right? Third one is existence of odd electron species could not be explained. That means there are certain odd electron species like NO is there, NO2 is there. You are seeing that this is like 7 plus 8, 15 here, right? And here 16 plus 7 electrons, 23 electrons there. So the existence of such kind of species could also not be explained. So that was one of the limitation. Now you must know that this theory was based upon the inertness of those compounds, inert gases. But the thing is, later on, after many years, what happened? There were certain compounds of certain inert gases which were found. That means what? They are able to react, right? So if they are able to react, so the entire basis of the theory is gone. So that is one of the major limitation of it. But still, this theory, it is still valid for, second period elements. Okay. So we're writing inert, or else we can write down this theory was based upon inertness of noble gases, but later on certain compounds of krypton and xenon were found. Like XeF2 is there, XeOF4 is there, you are having KrF2, right? So this entirely shook the basis of this theory. Please write this. Yes, I hope this is clear. And we are ending our session here itself, because in your Sunday's test, and I think whatever is your another exam on Tuesday, it's coming up to this only. So make the revision properly, read each and everything properly here, and you'll be able to excel in the examination. Okay. So wish you all the best for the test. Thank you and have a nice day.